All right.
I got halfway through. Always kills me. A lot of the questions. There were 2 questions on 17.5 basic that I read. There's gonna be every other question. She does it every single time.
I think we'll get down there pretty quick. This won't take real long. This is really cool stuff. Very important. I want to show you something interesting. Calculus informs us about the way the world works here. This is good stuff.
And I think today, we might get to finish with topics. I thought this week's class was kind of fun.
Okay, real quick. Let's try to zip through this. So I know some people still have some tests they need to be finishing up and whatnot. We can take a look at one of the rules that sort of governs the way the world works here, and we can understand why it works, and that's really what's important here with calculus. Look at this really simple idea here. If we take y is just going to be the dependent variable. Typically, it's going to be something like a population, but it might not be. It might be something like the number of plutonium atoms in a sample or something like that as well. Okay, k is just some constant. Think what that means. Ponder that for a second. I want somebody to try to give me a qualitative understanding of what that differential equation represents and why it makes sense. It really does make sense too.
What is k?
K is just some constant. Just some constant. So pretend y, let's just take y to be a population. It's a population of lemmings in Sweden. So what is this? What is dy dt?
Like how much?
It's y in relation to time subsidies.
Okay, it's a rate of change of the population, right? Okay, how do populations change? How do they grow? They have, yeah, I mean, well, okay, that's what we're maybe going to find. But they have babies, right? Okay. K is just some constant, and y is the population. So what is that saying? Another way of writing this that's a little less mathematical would be this. You know what that symbol is? That's proportional to. And whenever you write proportionality, really all that's saying is it equals k times that thing, right? So k is what we might call the constant of proportionality. Thank you. Or in our case, it's not really a. It's not really a. Well, yeah, I guess it is. It is a constant of proportionality. So, what's that saying, and why does that make so much sense? The rate of change. I'll get you started. The rate of change of the population is. Come on now, fill in the blanks. Well, okay, I mean, we might see that. That's not what that says. The rate of change of the but it's not constant. It's a constant, but it's being multiplied by y, which is the population.
It starts somewhere, right?
True.
So like that's the constant.
Well, the constant just tells us. I mean, we'll see where the constant comes into play, but would the rate? Let me ask you this: would the rate of change of the population be greater or smaller for a large population? Greater. How come?
Because each time it has babies, it keeps growing.
Okay, but in terms of this, you're right. Logically, you're right. But in terms of this equation, defend your answer. You're right. The rate of change of the population is going to be larger if the population is big. Why? Look at that simple equation and tell me why. Because it's proportional. Yeah, right? It depends on why, doesn't it? So now let's put those two ideas together. Really, all we're saying here is that the rate of change of the population is proportional to the population size. Sure. Doesn't that make sense? The more adults you have to have babies, the more babies you're going to have, right? Makes sense. If you have 10 times as large a population, you would expect the rate of change of the population to be 10 times as big. That seems so simple that it can't be profound. But it tells us something pretty remarkable. If we just start with that really simple premise, which, I mean, we can all agree that's true, right? If you can ignore other pressures on a population, like say there's a limited resources or something, and that does change by the way, and I'll talk a little bit about that. That does change the dynamics of population growth, but at least initially, and this is something I've kind of looked at, I'm interested in. If you look at population growth, initially every population behaves according to this rule. Eventually, things can change. Eventually, like with lemmings. Lemmings, they live in they have population cycles that go up and down. Rabbits do the same thing. Where the population will explode, and then they run out of resources, and predators start to take over, and then they plummet. They go up and down and up and down. I think with lemmings, it's every 7 years, I think it is. But initially, there's no pressure on the population, so they just grow according to this rule. Now, think what this implies. If the rate of population growth is proportional to the population size, and K is a constant that is positive and bigger than 1, doesn't that mean that that's kind of a runaway train effect, right? I mean, that's why obviously things have to come crashing down eventually, right? And we'll take a look at the graph of this here in a second too. Same thing is true with exploitation of resources. If you look at, there's a guy at University of Colorado Boulder, what is this guy's name? Can't think of his name, but he's a physicist, and he's kind of the foremost expert on that topic, on exploitation of finite resources. If you look at anything like the water table or petroleum, use of petroleum products, it always follows this normalized curve where it goes like that. This is the part that we're looking at right there, where there's no pressure on anything. But as soon as, and I tell you, I don't want to get off on a huge tangent, because I certainly could on this one. If you look at, for example, like fossil fuels, what you find is that as soon as, for any kind of a finite resource like that, when it starts to get complicated up in here, when this model has failed long ago, what you start to see is that as soon as it becomes economically unfeasible to extract the resource, people stop doing it. And so what always happens, and this will happen with petroleum products too, is that when you get to about this point right in here, all this petroleum right here gets left in the ground because the whole thing crashes down when it becomes too expensive to extract and the market collapses. And then this huge infrastructure is no longer supported. Now, what's really scary about this, and I'll just tell you where a lot of experts think we are, and we don't need, maybe later on we can have a discussion about this, but where do you think we are in this cycle, by the way, which is pretty scary? We're probably right there, which is pretty scary. So, and here's my plug for pushing for massive investment in alternatives. And by the way, nothing will ever replace fossil fuels. I mean, you can't swing a dead cat without hitting 14 things that are made of petroleum products. In this room, modern agriculture is essentially the product of, the process of turning petroleum into food. I mean, all the fertilizer we use is nitrogen-based fertilizer is all petroleum. I mean, it's going to be a bad deal, but we can mitigate minimize the losses a little bit if we can kind of push towards some other. But we're getting near that cycle. We're getting near the point where it's not going to be financially feasible to extract this stuff anymore. It's getting too hard to get to. But anyway, I won't go off on that tangent. If you're interested in this, though, starting to understand that really all comes from that one simple equation. So let's do a little calculus with it. So if we wanted to solve that differential equation, what do we do? And there's another little mini lesson that's kind of wrapped up in this. What do you think? This is a little different looking differential equation than what you're used to, isn't it? It's different because it's got y's in it too. It's not just, typically we're used to seeing something like, like this maybe, dy dx equals x squared, something like that. Where we're able to just multiply both sides by dx and get all x's on one side and dx, and then just plain old dy on the other side, right? And real quick, what happens if let's just bring that one to completion. What if we want to solve the differential equation dy dx equals x squared? Good review. What do we do to solve this differential equation? Multiply by dx. Now what?
Integral.
Yeah, now we undo the derivative by taking an integral, or antiderivative, whatever you want to call it, right? And then those cancel. the inverse processes, right? So we end up with y equals whatever that is. And what is that? Yeah. Good. Good. Plus some constant, right? That's how we do that one, piece of cake. Okay, the differential equation that I've just given you, though, is a little bit different, right? The rate of change of y is proportional to y. Now, what's the problem with this? If I multiply both sides by dt, well, yeah, what do I get? If I multiply both sides by dt, I get dy equals ky dt. That's the problem. I have two variables on the right side. So what do you think I do? Okay.
Hi.
Heard you had an accident.
Huh? Yeah, look.
Yeah, it's bad.
The bottle.
Okay. So what do you suppose I do? Say it again? Yeah, we got to move the y over to its own side. Now, there's a name for this, by the way. This is your first, just scratching the surface of dealing with something called a separable differential equation. Okay. So when you get something like that, our goal is we want to separate the variables each to their own side. So each side is homogeneous. We don't want to mix them up. Okay. Now sometimes you can't do that, and that's a college topic. Okay. But we can do it here. We can divide both sides by dy. What do you suppose you do next? You're going to be right. Yeah. Now we're just going to integrate both sides to undo the derivatives. Remember, the goal, or another way of saying it, the solution of a differential equation is what we get when we undo all the derivatives. It's the equation that we would differentiate to produce the differential equation, right? So we're trying to reverse all these derivatives, which we do like that. Okay, what do we get on the right side is the easiest. Let's do the right side. What do we get? Remember, k is a constant. Kt plus some constant, right? Okay, so on the right side, we get kt plus, we'll call it c2 for the right side. Okay, what about the left side?
Y over y dot.
Okay, now what's that one again? Think about that one. Well, but that's one of our new ones. You may not be quite as used to. Now, some of you guys that have worked ahead on the assignments, Nick, you know this one. What's our general rule? What's the antiderivative of du over u? Yeah, good. Natural log, right? Okay. So that's natural log absolute value of u plus c. But for us, we don't really need the absolute value, do we? Because y is a population, and a population can't have a negative number of people or a negative number of atoms or something.
Right.
It's always positive. So we just get natural log y plus, call it c1. Okay, now we might as well consolidate all the constants into one though, agreed? So we'll just subtract c1 to the other side, and c2 minus c1 we'll just call c, how about? So we end up with then natural log y equals kt plus c. Okay, that's our answer, but that's not a very satisfying answer. If we want to build a model, we want to build the model for y where it's not gobbled up inside a log function. We want to have y equals, so we can just substitute values for t and get answers, right? So what's next? How do we extract that y? How do we isolate the y here? And this is more of a last year topic. We briefly reviewed this, but how do you undo, say it again? Okay, we're going to exponentiate both sides. Good. So we're going to do this, literally. We're going to take e to the power of
Thank you.
both sides, right?
Yeah.
E to the log y is what?
One.
Y.
Why?
Yeah, they undo each other, right? Exponential function and natural logarithmic function are inverses, and so they undo each other. And so we end up with, here's our y by itself. Now what do we get over here?
No.
Well, we're getting
to the base.
e to that, but now if we use our property of exponents, if I have something like a to the
Oh.
m plus n, what's that equivalent to? What's another way of writing that? A to the m, I heard. Times, good. Very good, times a to the n, right? So I can split this up into a product of two exponential functions, or exponential factors, right? So we end up with e to the kt times e to the c. But e is a constant, e is the natural number, 2.7128, blah, 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 something like that. So e to the c then is also a constant, right?
Yeah.
Okay, so let's call that, let's say we called this one C3. And we'll just call e to the C3, we'll just call that C, how about? Okay? So look what we got. We got something, we started with our differential equation. And we ended up with a model. And in fact, we can see now it's an exponential model. Now, we know what this looks like. If we were to graph this thing, it just looks like this, right? That's our exponential model. Now we're going to start there, right? But that's that exponential growth model. So you can see that unbridled population growth is truly exponential in nature, which is kind of scary.
Can you go back to page for a second?
What's that?
Can you go back?
Sure.
really quick?
Sure. Go down.
Yes.
Maybe we can even figure out what the meaning of that big constant out front is. We know what k is, right? K is the constant of proportionality that governs the relationship between the rate of change of the population and the population size. So for animals that have lots of babies and have, generation after generation, K is going to be a high number. For people, it's a relatively small number. Adult people don't have that many kids, and so K would be a smaller number. That make sense? But that's going to be, K is going to be a constant that is affected by, environment, kind of animal. Maybe it's not an animal. Maybe maybe we're talking about the growth of water crystals in the bottom of a lake or something. Who knows? But there's going to be some natural constants that affect K. What does C mean, though? Let's go back to this picture here. What does C mean? Now remember that Y is a function of what independent variable? T. Good. So it's probably best, actually, to write this as Y of T is equal to C e to the kt.
Yeah.
If we want to explore the value of C, what might be a good number to substitute in for T?
0.
0. How come? It seems like a good number. It typically is, but why in this case is it so good? Look at this part right here. E to the kt. If T is 0, what is e to the kt?
1.
Yeah, anything to the 0 equals 1, right?
So that's why you're gonna find C.
Yeah, so if we plug in y of 0 equals c times 1, so c is what then?
0.
No,
Or
what does it
y
mean?
C is C.
is correct.
Okay, but what is it, so this went away, right? When I plug in 0, e to the 0 is 1, and we're left with just c. So y of 0 equals c. So c is that thing. What is y of 0?
Starting point.
Yeah, it's the initial population size, isn't it? Or the initial size of the sample, if it's not a population, right? So really, the best way we could write this then would be y of t equals y naught e to the kt. Okay? And, when we say not is just our way, that's, I don't know where that came from. I think it must be an English thing. But not means zero. So whenever you say something like,
George here.
you know, like X naught or Y naught or something like that, you're talking about the initial value of that quantity. So there's our model. That's pretty cool, right? Okay. Now, what if we want to know, for example, we want to know the doubling time for a population? And really now we leave the calculus realm and we're just into analysis. The calculus gives us that model. And I'm not saying we wouldn't do some calculus in exploring a model like that, but we don't really need calculus to do a lot of this stuff now that we've got our model, our growth model. It's growth, of course, if K is positive, but if K is negative, what's that going to do to this e to the kt part? Drops it to the bottom, doesn't it, right? It's creating a fraction where the growing part is on the bottom of the fraction. So does it make sense that that would be K? That's going to function, and that would look more like, if this is growth, then you guys all know this. This is decay, right? Decay is rapidly initially, and then it tails off, right? So this is an example of what happens with a radioactive sample, right? Initially, it falls off pretty quickly, but then it never really goes away completely, okay?
Because it has half-lives and
Exactly.
bigger to lower.
Exactly, yeah. And so if we wanted to do something like that, find a half-life or find a doubling time, what could we do if we start with this model? Y of t equals y naught e to the kt. If we want to find the doubling time, what could we do? What's going to happen at the doubling time? Think about that. What does doubling time mean for a population? Say it again. When the population is doubled in size. Compared to what? Its initial value. Okay, so what would the value of y be when we hit the doubling point?
Twice of what y naught is.
2y naught. Everybody agree? Okay. So if we're finding doubling time, we'd end up with 2y naught equals y naught e to the kt. How would we, and what we're really trying to do is solve for t, right? So how do we solve for t here? Okay, sure, but first what do we do?
Get it by itself.
First we got to get the exponential function, by itself, right?
Because you have to do addition.
So how do I get rid of that y naught? Okay, now there's something there that happens interesting.
Because it cancels.
Yeah. Okay, now I want everybody to see this. I know we're getting kind of near the end here, but this is pretty cool stuff. If I divide both sides by y naught, look what happens. The y naughts cancel. Is that strange? So we end up with the result e to the kt equals 2. That's really profound in a way. The math gods are telling you something important when they tell you that. How come the y naughts disappear?
Because they're constant. Not constant, but they're equal.
They're equal, but on a more theoretical level, the math gods are telling you something pretty important. They're telling you that doubling time is independent of population size, right? If a quantity disappears from a relation, it must not be impactful. It must not have any, it doesn't have any effect on the final result. Doesn't that make sense? If you're talking about doubling time, you're just talking about when a population of arbitrary size doubles. Could be 10, it could be 1,000, right? Okay, isn't that kind of cool? I mean, when you see how this stuff, that's how the equation kind of, it just dovetails with what has to be the case. So now what do we do? Now we can roll into analysis mode, and how do we solve for t here? How do you undo exponential?
E to t plus e to
Natural
t.
log, yeah, right?
Yeah.
Okay, so we get natural log of e to the kt equals natural log of 2. And what is the natural log of e to the kt? Kt, right? Equals natural log 2. And so t, doubling time, right? So we'll call it t sub d equals, yeah, natural log 2 divided by k. sense? Okay.
Yeah.
Good. There's a little rule. This is kind of good to know. I wish we had just another couple weeks. It'd be nice to have, but well, we don't. If you ever want to look at, this is something to remember. This is kind of a rule of thumb. If you ever want to estimate, when people talk about population growth, a lot of times it's very, very misleading. People talk about things like, or growth of anything, growth of the economy, people throw these numbers around. And they might say something like, well, we need some modest growth in Pendleton. Maybe they're right. But if they say, we don't want anything major. We just want something like 10% growth, population growth, okay? That doesn't sound, 10% doesn't sound horrible, right? But when you couch a growth statement like that in terms of a percentage, and you might remember from past years that if you have some kind of exponential growth that looks like this, y equals a times b to the x or b to the t. Let's make it b to the t. And for us, the base is just the natural, is e, the natural number, right? E. But when you have something like that, you can either write it, this is the constant multiplier, right? You can either write it that way, or you can write it as y equals a times 1 plus r to the t, where r is the percent growth. So for example, if the constant multiplier is 1.2, then that's equivalent to 20% growth. If every time you go through a year, the population is being multiplied by 1.2, does that make sense? That's 20% growth. Okay, so when you talk about something like 10% growth, what's really good to do is to use the rule of 72. It's a really handy way to look at this. If you divide the percent growth, or divide 72 by the percent growth, that gives you the doubling time. So now let's just think about it, and isn't that cool? It just does. It just does. So if you think about 10% growth, then 72 divided by 10 is approximately 7, right? So that's telling you that every 7 years, if you had 10% growth, you'd be doubling the size of the population. Now just extrapolate into the future a little bit. Think about what that would look like from your perspective later on in your life. Look at sleepy old Pendleton. So 10 years from now, what's the population? About 18,000, something like that?
16,
15
19.
to 16.
Who knows? Say, just for round numbers, let's just say it's 17, okay?
Okay.
So if it's 17,000, let's make it 17,000. Okay, so if it's 17,000, then 10 years later, so you guys are out of college, you're in your first job and stuff, so you're back and it's 34,000, okay? 10 years later, you're got, I don't know, you got young kids or something, who knows? That's weird to think about, huh?
Yeah.
So 10 years later, it's 68,000. Okay, 10 years after that, your kids are in, maybe elementary school, late elementary school, something like that. Pendleton now is, what are we at, 68, so now we're at 134,000, 136,000?
Wow.
Wow. Okay, your kids graduate from high school and are in college, and all of a sudden Pendleton is bigger than Spokane. Okay, your kids graduate from college and start their jobs, and all of a sudden now Pendleton is about the same size as Portland. Well, that's crazy. So do you see where this 10% growth, it's nuts. When you think of it in terms of doubling time, it's something you can sink your teeth into. It's really hard to think about it in
Is
terms
that
of a
really
percent.
how it's?
It really is, yeah, that's how it works, the rule of 72.
Wow.
Take the 72 divided by the percent growth, and that tells you what the doubling time is. And that's an easy way to think about a population or an investment in. What you guys should do, by the way, I'll make my little plug here and then I'll shut up about this. What you really should do, I'm just telling you, and you may not listen to me, but you should not blow your money on some crappy car that's only gonna run for a couple of years. What you should do is you should take as much money as you can. I know that's hard to do when you're going to college, but you should just invest some money in a fund that you are just not gonna touch. If you took a modest amount of money and you invested it in some kind of indexed mutual fund right now, say it's even just like $2,000. If you can, on a fund like that, long term, you can probably make something like, 10 to 15% at least. if you're willing to just leave it there for a long time. Let's say you make like 12%, okay? If you make 12%, what's the doubling time? 6 point something, right? What is 6 times 12 is 72, so it'd be about 6. So 6 years, and that's not great. I mean, you could probably do better than that, but say you did 12%. 6 years, so you start off with 20, so after 6 years, that's $5,000, right? After 12 years, it's $10,000. After 18 years, it's $20,000. 24 years, it's $40,000. I mean, this thing really starts to grow. If you could leave it in there for, 50 years, I'm sure you'd have $1 million in there. So and all it takes is just that minimal investment, but it's that power of compounding interest. If you're able to just leave it there and let it double, your retirement's essentially, at least partially taken care of, just from one, what would that be? What can that buy you now? Not very much, really. It's not, comparatively, it's not very much. So think about that. You can do it. It's the best financial advice I could ever give anybody because you're so young. Just put something away, even a modest amount, put it away and just don't touch it, and it'll make a big difference. All right. I don't really know what else I have to say about this. You know how you could use this model? I think this is probably good. You can use this model then once you get these numbers. Here it is. I mean, if we were asked a question like, when would, if you, say you were given something like a population starts off, so they're giving you y naught equals 100, and after 4 years, the population is 180. So, in other words, y of 4 equals 180. And I wanted you to tell me, what will it be after 10 years? What would you do? Yeah, okay. Do you see that in order to use this model, you got to know the values of the constants? Right? You're given one of them, aren't you? Right there. Okay, you're given y naught. That's the initial population size. If you want to find k, how would you do it? There's another point, right? You're really just given 2 points and you're solving for 2 unknowns. See how that works? Thank you. Oh, that's convenient. There's yours. Test that back. Everybody see this? So we get y of 4 equals 100 is y naught. E to the 4k. Everybody see that? The only unknown here, I know what this is. This is 180. And so the only unknown is k. I could just divide by 100, log both sides, and right? Does that make sense?
Yeah.
So we'd end up with 180 over 100 equals e to the 4k. So what is that? 9/5? Right? Yeah. So if I take a log of both sides, I get 4k equals the natural log of 9/5 divided by 4, and we got what k is, right? Now that I know what k is, I can plug in that value and that value, and we can plug in any value we want to for t and get an answer. So we've established our model. Does that make sense? Okay. All right. I'm done. I think that's good.